Welcome to lecture number 34. So today we are going to discuss the orientation and shape of some of the hydrogen atomic orbitals. So last time we have discussed about the wave functions corresponding to n is equal to 1. So today we start with n is equal to 2. The wave function corresponds to psi 2s. So there are two situations for n is equal to 2. The possible n values are 1 and 0. So we start with n is equal to 0. For n is equal to 2, n is equal to 0, this becomes the entire wave function. This is the radial part and this is the theta phi part. So as you can see that okay, so here for it should be 0, so it should be y 0 0. Okay. So as you can see that not surprisingly that since this is a case for both L is equal to 0 and M is equal to 0, so the angular part is independent of theta phi. Okay, so basically the wave function is dependent on the radial part. So that means the orientation of this function is basically spherically symmetric around the nucleus, okay, because it is only dependent on the radius. Okay, so that radial part is uniform in around 360 degree. Okay, the spherically symmetric 3D angle. So now can we try to find the average radius for n is equal to 2, n is equal to 0 value? That means the average radius of 2s orbital. Or in other words, the what do you expect the value of the electron when it is the average value of the electron's position when it is in the 2s level? Okay, so you can figure it out yourself and then try to compare with r is equal the average value of r1s. Okay, and let's see if you can find relationship between the two. And then we come to the L is equal to 1. So now the spherical harmonics part will appear. So we have two scenarios. One for m is equal to 0 and another is for m is equal to plus or minus 1. So we'll come to m is equal to plus or minus 1 value later. Now let's talk about m is equal to 0. Okay. So interestingly, now it is a function of cos theta. The first question comes to our mind that in which direction this or in other words the orbital that we would eventually get from this wave function, the question is, does that orbital have any directional property? So we can write this question here, that any directional property, or in other words, what is the orientation of the orbital that we are going to generate from this part. Okay, that means from RR20 Y10. So that is our question, the first question. And then second question we would like to ask that if we are successful in generating the orbital, what would be the shape of it? Okay, so to determine the directional orientation of the wave function, okay, or any wave function, we actually take the help of a plot that is called polar plot. Okay, so in this lecture today we are going to discuss in little detail about how to obtain a polar plot. Okay, so to obtain a polar plot, first we have to develop a series of theta versus cos theta values. So what I want to say that here we make a table. So theta value first, and then f is equal to cos theta value. So let's see for different values of theta, what would be the values of the cos theta. Okay, and then we will try to plot these cos theta values on a radial graph paper. Okay, so how it is done, then we would gradually discuss step by step. But before that, I want to draw your attention that here, when theta is 0 degree, okay, so the cos theta becomes 1, and also when theta is equal to 90 degree, cos theta value becomes 0, and when theta is 180 degree, the cos theta value becomes -1. Okay, so these values tells me that whatever the plot that we are going to get from the polar plot, uh, 0 means the function vanishes at a 90-degree angle. So that means on that plane we can expect a node. And not only that, the sign changes whenever we go beyond 90 degree. Okay, the sign gets reverses. And looking at the values of the cos theta going like this, 0, 90 degree and 180, and the cos theta goes 1, 0, -1, the direct correlation tells me that the orbital we are going to get from this wave function, okay, so we can write the represented orbital. Why I am writing represented? Because this itself not an orbital though, because it's a spherical harmonic, but the orbital at all it would represent, it's going to represent, so that represented orbital would lie along the z-axis. Why z-axis? Because according to our definition of the polar plot, if you remember, okay, so this is xy plane and this is z-axis, all right. So the angle that it makes vector with respect to z-axis, so something like this r. So this angle is theta, all right, and the phi lies on the xy plane, and this function is independent of phi. Once again, I repeat, this function is independent of phi, and it has only cos theta value. It is only dependent on cos theta as a function of theta, not sin theta cos theta or sin theta. So we expect that the represented orbital is going to lie along the z-axis. So this polar plot would going to represent, okay, or the orbital, the represented orbital would be nothing but a pz orbital. So that's how the direction among the three p orbitals, the pz orbital was first determined from the polar plot or from the nature of the cos theta dependent function. Okay, is it clear? Good. So now I am going to clean the board, and I'm going to show you how a polar plot is generated from where the orientation of the pz orbital can be obtained. Okay, so that's what I'm going to do next. Okay, so let's follow it. Okay, so now let me explain the polar plot in the most simple manner. So first let's make a table of theta versus cos theta. So whenever theta is equal to 0, 20, 40, 90, 180, etc., we have the cos theta values of 1, 0.94, 0.77, etc. up to -1. So now the polar plot is drawn on a special type of graph paper. So in the graph paper, there are radially oriented straight lines, starts from 0. So that is the value for cos theta. So cos theta is 0 here, and gradually it goes up from here it is 0.5, 0.6, 0.7, 0.8, and up to this is 1.0. And then the values of the cos theta, okay, actual values of cos theta on the theta values are drawn along this uh, kind of segment of a circle. Okay, so this is the arc. So this arc can go around 360 degree, but we are only concentrating on an arc that spans from 0 degree, so here is the theta value, so 0 degree up to the 90 degree. Okay, so now let's try to plot those or locate those points on this radial graph paper. Okay, so our first coordinate is theta is equal to 0 degree. So for theta is equal to 0 degree, we have the cos theta value. So these are the cos theta value is 1. So our first point is over here. And our second point for theta 20 degree, so this is a theta 20 degree line, and we go for the value cos theta 0.94. So the 0.94 would be, because so this is the 0.94 value, but here this will follow the exact same circular arc, so we are going to pick this point as 0.94. The next is 0.77. Okay, so 0.77 should be somewhere around here, but on 40 degree. Okay, so theta is 40 degrees, cos theta 0.77, so that cos theta value can be found somewhere over here. Okay, on 40 degree, and so on. And next we go for 60 degree. For 60 degree, cos theta is 0.5. I have already drawn, so here we will find the point over here. So now if someone goes for the complete range of theta versus cos theta, when we go for from 0 degree to 90 degree, okay, so by plotting all the values, we are going to find a beautiful semicircle, something like this. Okay, and if we complete on the other side, that means the negative values of uh, the theta values. Okay, there is a minus 20, minus 40, minus 45, so on. We will also have this. Okay, so I'm going to draw the circle like this. Okay, so roughly, approximately, we have a circle like this, and then again we have to go beyond 90 degree. Okay, so when we go beyond 90 degree up to 180 degree, we will have another uh, circle over there. So as a result, we get the polar plot something like this. Okay, so this is uh, the value of cos theta, of course, and this is -1, and this is +1, this is 0, and we have two complete and perfect circles like this. Okay, and also this. So pardon me, and they should not uh, overlap with each other. My drawing is not perfect, but you can imagine we can draw a circle like this. So they would meet exactly at the point over here, and that value is 0. Okay, and everything within this circle, the phase is, we can see positive, and everything in this circle, you can see the phase is negative. Okay, so this is nothing but the polar plot of pz orbital and obtained from y10 theta phi spherical harmonic. Okay, now what I'm going to say that in many textbooks you will see, so what you will see, now I'm telling you that whatever the polar plot that you have got, so remember this is not a cross section of orbital, not an actual shape, but this is a polar plot. But it is possible to make the 3D shape of this polar plot. Okay, if we make that, it will take up something like this. So maybe that's why I'm saying that in some textbook you will find a plot like this. So this is maybe x orbital, y x-axis, y-axis, and this is the z-axis. So you may find something like this. Okay, as pz orbital. So this is the z-axis. Okay, something like this. Yep. Okay. And this is also called the tangent sphere diagram, or the tangent sphere representation of PZ orbital. Okay, so it is possible to generate 3D shape from the polar plot, but this is not the exact shape of PZ orbital, because I can say that the 3D shape is inaccurate. Means that this is not the shape of the orbital. Okay, why is it so? Now let me tell you that what we have drawn the polar plot is that we have generated from the spherical harmonics. So this is what? So this can be best represented that this is the shape of the angular part of the PZ orbital. Okay, so let me write it here once again. This is actually the true representation of the shape of the angular part, the shape of the angular part of PZ orbital. Okay, and what are those? These are two perfect spheres, okay, barely touching each other. And this is the nodal plane. The node lies here. So, as an orbital, we understand the shape. We should understand that the shape of the polar part of the entire, wave function, not the angular part. So that's why you will see later the actual shape of the PZ orbital would somewhat differ from this. The reason that we would include the radial part of it. The moment we include the radial part, this shape, the actual shape, would differ from this, double sphere shape, and it would take up something like this. Okay. Let me try to draw as best as I can. Okay, something like this. So from this to this, if we include the radial part. So how we can draw, how the shape is obtained like this, the actual shape. So that's what I'm going to talk about next. Okay, so now I'm going to clean the board. But before we proceed, so let me tell you once again to show that why generating the 3D shape of the orbital from the polar plot, although you can, it is possible to generate 3D shape of the polar plot. Generating that would give you an inaccurate picture of the actual orbital. I will tell you with another example. Okay, after that we will come to the actual shape of the orbital. Okay, so let's do that. So now the example that I wanted to give you is y20 value. So y20 means L is equal to 2, and you can easily recognize that we are talking about the d orbital, okay, or the d level, and m is equal to 0. For that, we again get a function which is also dependent on cos theta. Okay, so again we can generate theta versus cos theta value. Now remember, it is cos square theta. Okay, so if we try to draw the polar plot, the actual polar plot would look something like this. So let me try to draw. I'm not very good at drawing, but still I'm going to try. So it would come up something like this. All right, and then here again we have two nodes in the xy plane. All right, and the signs would be like this, and they alternate, minus to plus, plus to minus, minus to plus. So that means there are two nodal planes lying along this direction, and we can tell theta is equal to 0 degree, here theta is equal to 180 degree, and this is nothing but this is the z axis. So again, no doubt the orbital lying along the z axis, and therefore it represents the dz square orbital. But the problem is, from this, if we try to generate the 3D shape, so if we try to generate the 3D shape of the polar part, the 3D shape is highly inaccurate because the radial part has not been included here. It is only the representation of the angular part. But are the polar plots any good? Of course, because the polar plot helps us to identify which is px orbital, which is pz orbital, which is dz square orbital, which is dx square minus y square orbital. Okay, so the utility of the polar plots is it helps us to identify the direction or orientation of an orbital represented by the spherical harmonics. Okay, so now I'm going to talk about the concept of orbital in terms of probability, how the actual shape of the orbital is obtained. Okay, so let's do it. Okay, so here now we would go for the probabilistic interpretation of the orbital. Mathematically, the orbital is defined as the probability of finding an electron over a finite space. Okay, so now how much is the probability in what location? Actually, that would govern the shape of the orbital. So to draw the shape of the orbital, there have been two approaches. One is called the dot plot, and another thing is the cross section of the contour diagram obtained from the dot plot. Okay, so or yeah, this is actually called the cross section of the 3D plot. Okay, so we'll come to that later. So first the dot plot. So the dot plot represents actually the plot of chi star chi theta. Now from our knowledge what we have obtained, that chi star chi is the probability density, fine, and the theta is the volume element. So what happens is, now I'm directly reading from your textbooks. Okay, so the textbook says the quantity chi star chi theta is the probability that the electron is located within the volume element theta. Thus, one can divide space into little volume elements and compute the average or some representative value of chi star chi within each volume element, and then represent the value of chi star chi by the density of dots in a picture. Okay, so these are the textbook languages to define the dot plot. So in simple manner, what we are going to tell you that the dot plot is generated when the probability density is represented over small volume element. And if we going to do that, if we try to do that, it ends up in putting a dot somewhere. Okay. So let's first try out the 1s orbital. So 1s orbital would give you dots like this. Okay, in all spherical 360 degree, and that would represent the 1s orbital. And then if I going to draw 2p orbital or 2p0, so it would look something like this, the way I am representing it. So this is the way of putting the dot plot, and then so you see the maximum density is located somewhere here. Okay, for a 2p orbital, and for 3p orbital this is going to change. Okay, so as you see, and there is no probability at the middle. So as you see, this is a this represents a sphere shape. Okay, so sometime we, represent this like this. This is a sphere. So sphere is the shape of the orbital, but what we say that the dot plot, the probability dot plot is something like this, and this is represented sometime like this. Okay, so this is the actual representation of the orbital of the, considering both the radial and angular part. And not only that, what we can tell that the density of dots represent the probability. So here you see we have more density here, less density here. So the density is what? So the density of dots, okay? Density of dots represents the probability of finding the electron. So that means what? That where the density of dots is more, like this area, so the probability of finding the electron this area is more, so rather than that area. So here also you see the probability of finding the electron right near the circumference, okay, is more. So that's how the dot plot is generated. So remember, it is the probability density basically, the orbital. So where the probability density is more, that means we have more chi value, the probability of finding an electron is there. And the way it distributes itself in the 3 dimension means overall the volume element, it represents the shape of the orbital. Okay, so by doing the dot plot, one can know the shape of 1s orbital, one can know the shape of 2p orbitals. The same way, one can understand the shape of 3d orbitals also, 4f orbitals, etc. Now, the another way is the contour diagram. So the contour diagram is nothing but the cross section of the 3D plot of the chi star chi. So if you take the cross section of this p orbital, so then you will find the cross section will give you some contours. Okay, so it is just like if you take a cross section of a log of a wood. Okay, so the cross section would tell you something like this. That means the density is more here and it is lighter outside. So the detailed diagrams or pictures are given in your textbooks, quantum chemistry textbook. So you can follow the pictures to have a general idea of the dot plots and the contour diagrams. All right. So with this, now we have a general idea about the orbital. So remember, both the polar plot and dot plot is needed to understand an orbital. Why? Because the dot plot or contour plot would give you the shape of the orbital, but you need the information from the angular part, that means from the polar part, to know how this like a dumbbell shaped p orbital is oriented. Okay, so if it's oriented along z axis, we call it pz. If it is oriented along x or y axis, we call it px or py respectively. All right, so with this we have now a brief idea about the quantum numbers and their significance, and wave functions, how to find the average values of different parameters, and then we came to know about the sizes, orientation, and the shape of the orbital. But still, there are few more aspects left. What are those? So let's take a look what happens at of the spherical harmonic y1 plus or minus 1. So that leaves us something interesting to discuss. Okay, so let's quickly erase and discuss about it. So now as you can see, the for y1 plus or minus 1, spherical harmonics where m not is equal to 0. So these are the two functions that I have written. But here the angular functions are difficult to represent graphically. Okay? That means the polar plot is simply not possible using this information. Why? Because you see that it contains both the angle theta and phi. It makes it very difficult. And not only that, it contains the imaginary quantity I. So how one can possibly draw a real plot? But ironically, if someone wants to make the contour plot or the density plot, he has to take the value of this. So that means this is nothing but the chi star chi plot. Okay. So that chi square plot actually give you the real values, because the chi star chi means even if it is imaginary, multiplying it with its complex conjugate makes it real. So therefore, it is possible, very much possible, to draw both the density means the dot plot and the contour plot. Okay, it is possible. So someone actually knows the shape of the orbitals for px and py orbital, not a problem. But the only major problem is, how do we know in which angle or along which axis the px and py orbitals are located? Whether these are going along, so if this is x and this is y, so the question is whether this is lying along the x-axis or whether it is lying in between x and y-axis like this. So that is the major question, how to do that. And not only that, this is an imaginary function. Okay. So once again, so we are coming to the point that we understand the shapes that determine the probability is nothing but comes from the probability density chi square. It will always give you real values no matter what. But the only thing bothering me is the imaginary part of the wave function, which stops me to draw the polar plot. So how to get rid of this? Okay, so to get rid of this, we have to represent, or we have to convert these imaginary functions into real functions, and then probably we can represent. The question is how it is possible. So it is possible once again by the help of mathematics. So I'm going to erase this and want to explain what is the step that is actually followed for transforming the real part, the transforming the imaginary part into some other equation which represents the same thing but as a real function. Okay, so what is typically done, that there is one property that if two eigenfunctions have same energy and their linear combinations will also be the eigenfunctions of the same Hamiltonian operator. So that means if I have y1 plus 1 and y1 minus 1, those two spherical harmonics, means these two are eigenfunctions, these are having the same energy that we know. So their linear combinations, means the linear combination of this plus this or this minus this, will be the eigenfunctions of the same Hamiltonian operator. So that means we can take the linear combinations of these and can represent a third function. The third function is equally capable of representing the some orbitals which has the inherent property of those spherical harmonics. Okay, so for example, if we take the linear combination of y1 and y1 minus 1 in this manner, and also y1 1 minus y1 minus 1 in this manner, so we will generate a function like sine theta cos phi and sine theta sine phi. And if we try to plot the polar plots, then we will find that this orbital or this wave, the orbital represented by this wave function would lie along px, and this one would lie along, lie along y-axis. So this would represent the px orbital, and that would represent the py orbital. So therefore, representing an orbital like this manner gives us a real picture and easily visualized directional property. Okay, so this way of taking linear combination works also for other orbitals. For example, we have to take y21 and y2 minus 1 into different way of linear combinations. Then we can obtain the polar plots of dxz and dyz, the directional properties we get. Same thing is apply on y22 and y2 minus 2, then we get the directional properties of dx squared minus y squared and dxy. So remember, if you open up any standard chemistry textbook, and in that textbook, either in the appendix or at the beginning, you will find a list of different hydrogen wave functions. Okay, so there you will mostly see that the wave functions have been represented in real form, like theta phi part, the sine theta cos sine phi or sine theta cos phi. You will never see, you will hardly see the imaginary part represented as the wave function. So how those wave functions have been represented, the real wave functions? So the real wave functions have been represented by taking the linear combination conforming to the mathematics. Now if you are really interested to know that how by taking a linear combinations of two imaginary quantities give you an apparently real quantity, for that you have to study some detailed mathematics which is beyond the scope of this course. But as of now, what we know, that although the actual solutions are imaginary, some of the solutions, but by taking a linear combination, we can represent them as a real wave function, and that real of wave function would still continue to serve as an eigenfunction of the Hamiltonian operator for the hydrogen atom. So with this, now we have a clear picture that how the wave functions are represented in hydrogen atom, and from the wave functions how we can get the idea of orbitals, its orientation, size and shape. Okay, so with this here we are now going to conclude the hydrogen atom. All right, so from the next lecture onwards we will study uh, the process of the approximation methods. Okay, so please study this chapter from the textbook, follow the diagrams, and if you have any questions, please don't hesitate to ask me. Okay, so we will see you in the next lecture with a beginning of a new chapter. So till then, goodbye.